Hello, my name is Dragan Veselinovic. Today I will be talking about NMR-based capillary pressure measurement as part of the More You Know SPWLA webinar series. This presentation is sponsored by H2 Labs. H2 Labs is a subsidiary of Green Imaging Technologies, where I've been involved in NMR rock core analysis for past 11 years. Green Imaging Technologies, or GIT, has built a reputation as a global leader in applying NMR technology to industry since its founding in 2006. The origins of the company include commercialization of NMR and MRI applications research completed at the University of New Brunswick's world-renowned MRI Research Center headed by Dr. Bruce Balcom. Green Imaging Technologies has two arms of business. One provides NMR technologies, including software, hardware, and accessories, and another arm that provides NMR analysis services, mostly for rock cores and rock cuttings. H2 Labs has access to a suite of NMR instruments, centrifuges, and overburden pressure cells and probes optimized for work on rock core plugs and cuttings. The outline of today's talk is as follows. First, I will talk about NMR well log calibration, which is a fairly standard NMR rock core analysis practice. I will then briefly introduce standard capillary pressure measurement practices. For more details on these measurements, I suggest you look up Jules Reed's Premier Corex webinar on capillary pressure, in which Jules does a wonderful job on summarizing current capillary pressure measurement methods. Lastly, I will talk about the NMR-based capillary pressure, which is Green Imaging Technologies, or GIT's patented technology. NMR can be used to measure air brine and oil brine capillary pressure. Once the capillary pressure curve is obtained, it can be used in other petrophysical measurements, which will also be mentioned towards the end of the presentation. So what is NMR? NMR stands for nuclear magnetic resonance. It can directly determine the amount of hydrogen in a sample. NMR instruments can be tuned to detect other nuclei as well, but in most applications, hydrogen is used. This is obviously applicable to oil and gas samples, since the samples are usually saturated with hydrogen-bearing fluids, such as water and/or hydrocarbons. Rock matrix usually does not contain a lot of detectable hydrogen, so NMR is mostly used to detect fluids in the rock. NMR can also be used to produce images. This is done by localizing the hydrogen signal by using magnetic field gradients. If used for imaging, NMR is referred to as magnetic resonance imaging, or MRI. NMR and MRI have a wide range of applications in many industries, such as food industry, medicine, petroleum industry, manufacturing, and so on. Most familiar use of MRI is in the medical field, where it's used to produce images of human body, like the 2D image shown in the bottom right corner of the slide, where we have an image of a human head. In addition to detecting a hydrogen signal and be able to localize it, NMR can also tell us something about the environment of hydrogen. For example, we can differentiate tissues in medical MRI and differentiate fluids in rock core experiments. How does this work? Well, the signal intensity depends directly on the amount of hydrogen, while the signal duration depends on the environment of hydrogen. Signal duration in an NMR experiment is governed mainly by T1 and T2 relaxation times. Let's now talk about the relaxation mechanisms that we mentioned, so namely T1 and T2 relaxation. When placed in a magnetic field, such as an NMR spectrometer, hydrogen nuclei align themselves along the magnetic field lines. The nuclei are then excited by applying a specific frequency pulse, radio frequency pulse or RF pulse. After the pulse is applied, the excited nuclear spins don't return to their ground states immediately, but instead they undergo relaxation. The easy way to think about this is to think of the excited nuclear spin that has been rotated by 90 degrees or from pointing along the positive y-axis to pointing along the positive x-axis in a Cartesian coordinate system. As the spin relaxes from pointing along the excited x-axis, as well as it relaxes back up, its y component grows back to the original value, and this is known as the longitudinal or T1 relaxation, while its x component shrinks to 0 and is known as transverse relaxation or T2. Longitudinal and transverse relaxations are both exponential decays and can be detected separately. The rate of these decays depends on the physical properties of the system being observed. Specifically, longitudinal decay is caused by the interaction of excited nuclear spin and its surroundings, while the transverse decay is caused by the interaction of the excited nuclear spin with other nuclear spins. Sometimes this is also referred to as a spin-spin relaxation mechanism. This can tell us something about the environment of the hydrogen. So inside rocks, T1 is typically 1.5 times longer than T2. In our lab, we mostly use T2 relaxation for well log calibration measurements. On the left side, we have raw T2 decay data from a low field 2 megahertz NMR instrument. Y-axis is the amount of signal in machine units, and x-axis is time in milliseconds. The data is acquired in 2 channels, real channel, which is in red, and imaginary channel, which is in blue. Before processing, data in both channels is rotated so that the imaginary data is parallel to the x-axis beginning at the origin. Consequently, the real data will have maximum signal at the origin, and this value is taken as the total volume or total porosity of the sample. The raw data can then be inverted using inverse Laplace transform techniques to give a T2 distribution shown on the figure on the right. On the right side, the x-axis is T2 relaxation time in milliseconds, and the y-axes are incremental and cumulative volume from left to right, respectively. The thick and thin red curves show incremental and cumulative volume, respectively. The total area under the thick curve is the total volume, normalized to the volume obtained from the raw data. The cumulative volume is curve. The cumulative volume curve is the integral under the thick curve. The reason why T2 data is so useful is because it can be related to the pore size distribution of the sample by the equation in the bottom right corner. So we have 1 over T2 equals 1 over T2 bulk plus rho, which is the surface relaxivity, times the surface to volume ratio, S over V. plus a diffusion term, which includes gyromagnetic ratio gamma, gradient G, echo time TE, and the diffusion coefficient D naught. As we saw on the last slide, the transverse relaxation time is related to the surface to volume ratio of the pores through the equation at the bottom right corner. T2 bulk in this equation is often large compared to the T2 in the pores. So the 1 over T2 bulk term can be ignored. Similarly, we are usually using short echo times in these experiments so that the diffusion term can also be neglected. This makes T2 inversely proportional to the surface to volume ratio. So small pores with large S to V ratio will have short T2 relaxation times, as shown in the left figure, where it says small. And large pores with smaller S to V ratios will have a longer T2 time, which are shown on the right side where it says large. The overall T2 decay, which we acquire in an NMR experiment, is the sum of all T2 decays from all the pores, large and small. In order to derive the pore size distribution from the overall T2 decay, we fit this decay to an exponential function and then invert the function to obtain the T2 distribution. Because T2 is proportional to S over V, the T2 distribution can also be thought of as the pore size distribution. In this case, having 3 peaks for the small, medium, and large pores. The NMR instrument is calibrated so that the y-axis is volume of water observed, and hence the sum under the T2 distribution is the pore volume of the sample being investigated. Once the pore volume is known, porosity can be calculated by dividing the pore volume by bulk volume of the sample. Here's an example of an NMR T2 distribution that you might get from a typical lab well-log calibration measurement. Historically, several samples were studied from different formations, and industry standard T2 cutoff values were determined for bound versus free fluid in a sample. For sandstones, the industry standard T2 cutoff is 33 milliseconds. For carbonates, it's 90 milliseconds, and so on. In the T2 plot shown, a T2 cutoff of 33 milliseconds is represented by the vertical red line. So everything to the left of this line is considered bound fluid, while everything to the right is considered free fluid. The reasoning here is that the fluid in small pores is harder to remove than fluid in large pores. No 2 rock samples are the same, so assuming a single T2 cutoff value for the whole well or reservoir can lead to errors. On this slide, I will talk about an alternate method to determining T2 cutoff for a rock core plug. So starting with a clean and dry sample, we first completely saturate it with brine. We then acquire the T2 distribution of the 100% saturated sample. This is the blue curve. The sample is then spun in the centrifuge to irreducible brine saturation. T2 distribution for the desaturated sample is shown in red. To determine the T2 cutoff, the peak of the thin red curve is extrapolated back to the thin blue curve, and where these two meet, a vertical red line is shown. This is where the T2 cutoff for this sample is located. So the T2 cutoff seems to be around 3 milliseconds for this sample. This is very different from the standard 33 millisecond cutoff for sandstones. And it means that if we use the standard value, we would greatly be underestimating the amount of free fluid. This sort of T2 analysis gives us a lot of information, such as bound volume index, free fluid index, porosity, clay-bound water, and so on. So the T2 cutoff workflow is listed here. We start with a clean and dry sample, saturate them with brine. We then measure a T2 of the fully saturated sample. We then spin the sample in the centrifuge to achieve irreducible water saturation, SWI. We then measure T2 of the desaturated sample and process the data to get the T2 cutoff. From the T2 cutoff analysis, models can be used to determine permeability. The permeability model equations shown on this side are the log mean model and the Coates or free fluid model. So the log mean model uses T2 geometric mean and porosity and the constant A to determine permeability K. The Coates model uses Coates coefficient and the ratio of free fluid index divided by the bound fluid index to estimate permeability. For a typical NMR log, we will have T2 distribution as a function of depth, and then we can divide that T2 distribution into free fluid and bound fluid using the appropriate T2 cutoff, which is represented by the red line on the well log figure on the slide. We can go one step further from that and plot permeability as a function of depth, again using T2 cutoff and the models I mentioned in the last slide to calculate this permeability. It quickly becomes apparent that the choice of T2 cutoff is very important for well log calibration. Okay, so that kind of wraps up the T2 discussion and well log calibration discussion. Let's now talk about the capillary pressure measurement. Capillary pressure is defined as pressure at the interface of two immiscible fluids. It is a combined effect of surface and interfacial tensions, pore size, geometry, and wetting characteristics of a given system. A simple illustration is shown in the bottom right corner. Tubes of different diameters and wetting properties are filled with oil and submerged into a water bath. Depending on the characteristics, the water column height is different for each tube, as well as the shape of the meniscus. Red tubes are water wet, while the blue tubes are oil wet. So you can think of these as glass and Teflon, for example. We can say that glass is red and Teflon is blue. Capillary pressure is a fundamental petrophysical rock property and plays a key role in understanding the reservoir. It's measured in the lab on rock core plugs. In a two-fluid system, three separate curves can be measured. These are primary drainage, imbibition, and secondary drainage. There are three traditional measurement techniques: porous plate or porous membrane, centrifugation, and mercury injection. They all have their pros and cons. Porous plate is considered the golden standard measurement, but the main disadvantage is that it takes a long time to do this measurement. Mercury injection is a quick and dirty method. Its disadvantages are that it's destructive, so the samples can't be reused after you've done the measurement. You can't reuse the sample. Also, it's using a non-representative fluid. In an oil and gas reservoir, we don't have mercury, so that's another disadvantage. And centrifugation method is related to the NMR capillary pressure measurement that I will talk about in the next few slides. So I will discuss that one in a little more detail. Again, I would recommend Jules Reed's webinar on discussing the details on traditional capillary pressure measurements for more details. Okay, so the traditional centrifuge method starts out with clean and dry samples. They're then saturated with brine and spun in the centrifuge at low speed. As the sample spins, fluid is expelled from the sample due to centrifugal force and collected at the outlet phase. Once equilibrium is reached, no more fluid is produced. This can take anywhere from minutes to days, depending on the sample permeability. The amount of expelled fluid is measured and the centrifuge speed is increased after the equilibrium is reached. This process is repeated at many different speeds until enough data points are collected for the capillary pressure curve. In modern centrifuges, the amount of fluid expelled is measured with a combination of strobe lights and a camera. Capillary pressure at the inlet is calculated by using the Hassler-Brunner equation, which is given at the bottom on this slide. And saturation at the inlet is a little more tricky to determine, as it has to be approximated from the amount of collected fluid, which only gives the average saturation. The equation for inlet saturation is given below. Average water saturation must be converted to the saturation at the inlet, as already mentioned. This equation cannot be solved directly, but there are a few approximate solutions, Hassler-Brunner, Forbes, and so on. Once the capillary pressure and saturation at the inlet are determined, capillary pressure curve is generated like shown in the plot. This data is from an air-brine capillary pressure measurement. On the y-axis, we have capillary pressure in PSI, and on the x-axis is saturation. In this particular case, 7 different centrifuge speeds were used to generate 7 data points. If it takes a day to reach equilibrium for each of these speeds, then this experiment would take about 7 days to finish. So this kind of concludes the overview of the centrifugation method. And now let's look at the NMR-based measurement. So NMR-based capillary pressure measurement, or GitCap, is a patented technique by Green Imaging Technologies, as I've mentioned earlier, and we actually call it GitCap. That's the name of the procedure. It relies on centrifugation for sample preparation. So many of the steps are similar to the centrifuge method that I discussed earlier. We start with a saturated sample and measure its saturation profile using NMR. A typical 100% saturated profile is shown in yellow over the top of the schematic of the core plug. We then spin the sample in the centrifuge until equilibrium is reached at a low speed and measure the desaturated profile. The desaturated profile is shown in yellow. As expected, we notice a saturation gradient, with the saturation being close to 100% at the outlet phase and much lower at the inlet phase. The desaturation profile is then divided by the saturated profile shown on the previous slide to obtain a saturation distribution along the core. This means that we can get many saturation data points with only one centrifuge speed, not just the average saturation, as was the case in the traditional centrifuge method. Capillary pressure is calculated using the same equation as in the traditional centrifuge method, except in this case, we use many radii corresponding to different saturation positions along the sample instead of just the inlet face radius, as is the case in the traditional method. Consequently, we do not need to use as many centrifuge speeds. Usually, only 2 appropriate speeds are enough to obtain the complete capillary pressure curve. Here's an example of NMR saturation profiles. The fully saturated profile is the purple one, followed by desaturated profiles below it. And these profiles were obtained after centrifuging the sample at 500 RPM, 1000 RPM, 1500 RPM, and 2500 RPM. The profiles are used to generate the capillary pressure curve shown on this slide. We notice that each centrifuge speed gives many data points. A quick cap fit is done on the data shown in the cyan color, and this represents the NMR measured capillary pressure curve or GIT cap curve. Porous plate capillary pressure measurement was also done on the same sample, and this data is shown in purple. As we can see, it agrees pretty well with the GIT cap data. So to kind of summarize the workflow for the air-brine protocol, we show this slide. We start with a clean and dry sample, saturated with brine, do NMR measurements, spin in the centrifuge at low speed, do NMR measurements, spin at high speed, do NMR measurements, and process the data at the end. As we see, there's a lot of overlap between the capillary pressure workflow and NMR well log calibration workflow. The highlighted steps are identical, so it would make sense to do these measurements concurrently since sample preparation is often the most time-consuming part of these experiments, or any NMR experiments for that matter. During the GIT cap validation study, some samples were not homogeneous and had a multimodal T2 distribution, like the carbonate sample shown on this slide. For inhomogeneous samples, the GIT cap data points are more scattered, which reflects the heterogeneity of the sample, but the average fit still agrees fairly well with the porous plate measurement. The bottom line is that more data in the GIT cap measurement gives more information about the sample. If we're only acquiring one average data point per centrifuge speed or porous plate, we may mask some of the important details in the sample. Over the years, we got many questions about what are the permeability limitations for this technique. As with any technique, GIT cap has its limitations. So the lowest permeability sample we tested successfully was around 10 microdarcy, which is fairly low. Here's an example showing a 12 microdarcy sample that was tested. Additionally, we can do oil-brine capillary pressure measurement. So naturally, following the air brine, we will discuss this measurement. The challenge here is how to distinguish oil from water, since they're both hydrogen-bearing fluids. A few different options exist, but the simplest solution turns out to be you just replace water with heavy or deuterated water, D2O. D2O is NMR invisible, so in a sample where we have oil and D2O, only signal from oil is detected. There are some issues with this, as D2O is not exactly the same as H2O. It has a slightly different density, and it can be tricky preparing the D2O-based brine because it's hydroscopic. If D2O is left to sit outside, it will absorb moisture from the air. And this is, of course, not good, as it can then become NMR visible, which is what we're trying to avoid. And it also becomes more hygroscopic at higher temperatures. So if we're dealing with higher than room temperatures, there could be some problems. The Oil-brine good cap protocol is basically the same as the air brine, except there are many extra steps. Once again, we start with a clean, dry, brine saturated sample. We measure the 100% saturated profile. We resaturate it with D2O, make sure there's no NMR signal after this step. After D2O saturation, the sample is ready for primary drainage steps. For primary and secondary drainage, we surround the sample with oil in a specialized centrifuge bucket and spin it. As the sample spins, D2O comes out, oil goes into the sample, and we can measure the oil saturation profile after equilibrium has been reached. For the imbibition steps, the opposite is done. So sample is surrounded with D2O brine, and as it spins, D2O goes in and oil comes out. To illustrate the oil and brine process, next few slides are shown. The first part of the primary drainage oil-brine capillary pressure curve is shown here. This is done after spinning D2O brine saturated sample in decane at a low centrifuge speed and acquiring the NMR saturation profile. The sample discussed here is a sandstone with 18.7% porosity and 542 millidarcy permeability. So here's the second part of the primary drainage curve obtained after a higher centrifuge speed. So after SWI is reached, and if reservoir oil is used instead of decane, the sample is usually aged to restore wettability. This consists of bathing the sample in reservoir oil at higher temperature and flowing a few pore volumes of the oil through the sample in a pressure vessel over a period of a couple of weeks. So this obviously will add a lot of time to this measurement if this step is necessary. After aging the sample, imbibition steps are done. The sample is surrounded in D2O and spun at a low speed. The yellow data points show the first part of the imbibition capillary pressure curve. The high-speed imbibition part is added to the plot of this slide, so we get a complete imbibition curve. After imbibition, secondary drainage commences. Once again, the sample is surrounded with oil and spun in the centrifuge. First part of the secondary drainage curve is shown in purple, and this is the second part of the secondary drainage curve, shown in purple once again. And finally, we end up with a complete oil-brine capillary pressure curve. This process takes about 5 weeks to complete for a typical sandstone sample, like shown in this slide. So during NMR capillary pressure protocol, we are taking samples out of the centrifuge to take NMR measurements. This raises the question, how much time do we have to do the NMR measurement before fluids start to redistribute after the centrifuge is stopped? So to answer this question, we saturated a fairly high permeability sample and acquired saturation profiles over the period of 3 days. It turns out the fluid redistribution is not a big factor even in this high permeability sample within the first hour. So with modern NMR equipment, it is definitely possible to acquire all necessary NMR data within an hour of stopping the centrifuge. So this is not as big of an issue. And it'll only get better with lower permeability samples because the fluid will redistribute even slower. Capillary pressure curve can be used to determine additional important petrophysical quantities, namely pore throat, NMR relaxivity parameter, and we can use it to model the relative permeability and USBM wettability. I will use the next few slides to show how this is done typically. If contact angle and interfacial tension are known for the fluids in the question, pore throat can be calculated from the capillary pressure curve. So this is shown in red. And we're converting capillary pressure to radius using the given equation there, R equals 2 times sigma cos theta divided by PC, where theta is the contact angle of the fluids and interfacial tension is sigma, and PC is capillary pressure, of course. Traditionally, NMR pore size distributions can be calibrated by comparison with mercury injection capillary pressure data. The MICP data gives the pore size distribution as a function of radius. The surface relaxivity, which is denoted by rho in the equation, can then quickly be determined from the MICP data if the pores are assumed to be cylindrical. Once the surface relaxivity is known, the T2 values can be converted to pore radius. So basically the same procedure can be used using the NMR-based capillary pressure measurement, where we replace the mercury injection pore throat data with the NMR-based pore throat data, basically. For USBM wettability, if we have a complete oil-brine capillary pressure curve, we can calculate the USBM wettability as the log of area under the secondary drainage curve divided by the area under the imbibition curve. So let's wrap up this presentation with a few takeaway points. Proper NMR well log calibration is essential for calculating T2 cutoff in well logs. As we saw, underestimating or overestimating T2 cutoff can have a huge impact on free fluid and bound fluid estimates in your well. NMR provides a fast, accurate, non-destructive method to determine capillary pressure. GitCap is easily integrated into NMR well log calibration protocol. As we saw, a lot of the steps for sample preparation are the same, so it would make sense to do these measurements concurrently. GitCap gives more data for each centrifuge speed, so it's easier to notice if there's a problem with inhomogeneous samples or some other problem. More data is usually better. Inlet saturation is measured directly as opposed to relying on simulation. This is especially useful for transition zones where we can use this methodology to measure T2 cutoffs in these transition zones, even where the water saturation may not be at SWI. The GitCap is successful on samples with permeability greater than 10 microdarcy. So yeah, this wraps up my webinar. Thank you for your time and attention. If you have any questions regarding the capillary pressure or NMR analysis in general, please don't hesitate to contact H2 Labs at the email listed here. Thanks again.